Today I present to you Lecture 5 of the FIR filter series. Last lesson we looked at choosing window functions, where we looked at the rectangular window. There are other window functions out there in the market, but they are a bit more complex to explain, but they are better performance. However, we did look at the rectangular window only because it's simpler to explain. And we also looked at multiplying window function with the impulse response. We looked at multiplying the window with the impulse response puts the window into effect on our signal. So if you can remember our impulse response, let's draw some impulse response. That goes to plus infinity to minus infinity. By applying a window function, so let's make a window function, we've actually put this impulse response limited in time. So now this doesn't go to infinity, this just goes to whatever our rectangle function limits us to. So imagine if the rectangle limits us to t equals 5 and t equals minus 5. This will be minus 5 and t equals 5 here. The rectangle function limits our impulse response in time. Now today we're going to look at, now if you remember, at the end of step 4 we get an array of filter coefficients. So let's do some rubbing out. Rub all this out. The result of step 4 is result an array of filter coefficients. So step 5 is using convolution to convolve the filter coefficients with the input, and that gets us the filtered output. So today let's look at convolution. If you like this content, please like and subscribe, and please comment any questions you have below and I'll be happy to answer them. Let's move on. Convolution. Convolution. Convolution is a mathematical operation which has the following formula. For an array convolution, yn equals sum of m minus 1, k equals 0, xn multiplied by an minus k. So let's decode what this means. M minus n. M is the filter order, a filter length. Filter length. K is the time delay. K is as we move in time, K will increase. After every iteration of this summation, K will go up. Okay, xn is the input signal. And finally, A is our filter, or A is an array of our filter coefficients. And it has this over here, means that the filter coefficients is shifting over time. This means one signal is shifting over another signal over time. Okay, oftentimes convolution is confused with multiplication, or people are struggling to figure out the difference between multiplication and convolution. So let's quickly take a look at that. So multiplication, let's get a pen. Multiplication scales a signal. It scales a signal for each element. So if you have two signals, so say our impulse response, and some other random signal that we want to filter. So we can call that signal 2, and that's our signal 1. If we multiplication, we are just taking each sample at each sampling point, so this would be n equals 1, n equals 2, n equals 3. And we just multiply, let's get a better pen, each value at each sample. So we'll take the blue signal at sample 1 and the orange signal at sample 1 and multiply them together. Do the same for sample 2. What's the value here? What's the value here? Multiply them together. What's the value here for sample 3 and value here? Multiply them together. And then you'll get an output signal that is scaled. So signal 1 is, so that should be signal 1, is scaled by signal 2. That's what multiplication is. However, with convolution, the difference is, well, let's remove this, is instead of just scaling two signals together, let's draw something. You're actually shifting one in time. So imagine this is signal 1, and we have signal 2. Signal 2 is actually moving. Signal 2 actually moves this way. So if for n equals 0, signal 2 could be here. And for n equals, well, let's just do a different color. N equals 7. Well, signal 2 has moved. Signal 2 again, but it has moved. So it's shifted from this position here to this position here. And we're doing mathematical multiplications whilst we're doing this shifting. So as it shifts, it's multiplying. And that's the difference. We're not just simply scaling signal 1 by signal 2. We are shifting signal 1 and signal 2. And this shows us the overlap, or we're trying to merge the two signals together. The result of convolution is typically the merging or overlapping of two signals. Let's take And this operation is known as convolution. Convolution. So to get a clearer understanding of array convolution, so in a computer you would be dealing with arrays, not just these random graphs, so that you have a clearer understanding. So this animation I'm going to show you hopefully will animate the convolution of filtered signal equals the summation of m minus 1, k equals 0, x, and multiplied by a, n minus k. This animation should explain what this formula basically does. So let's watch the animation. So can we see how as we move in n, so n is our samples, if you remember that, this filter coefficient is actually shifting. Each sample, after every sample, we shift by one element. And then we just multiply we multiply this element with whatever its corresponding input signal value is. And we do that for all of them. And this will just keep shifting, multiplying and adding, multiplying and adding, multiplying and adding. So let's just go back a little bit. Remember, it says xn multiplied by an minus k. So an, so the first value of y0, or the filtered output, the first element will be simply a0 multiplied by x0. When we move in time, you can just see that as we shift, we are just multiplying and adding new different values. And that is simply what convolution is. It's multiplying and adding a signal that is shifting over another signal. Hopefully, why did we look at convolution? Because the filtered output, or the output of our filter, is simply equal to the FIR coefficients convolved. This is the convolution sign. Convolution convolved with our input signal. And that's why we looked at convolution, because that is the last step to FIR filters. To apply your FIR filter onto your input signal, you convolve the FIR coefficients with the input signal, and that's it. That's all you have to do, and your FIR filter is complete. Now, so far in these lecture series, the recent lectures, we've looked at basic FIR filter parameters, such as filter cutoff frequency. We've looked at the filter function, such as low pass, high pass, band stop, etc. We've also looked at filter order. However, these are only basic parameters. There are actually more in the real world for FIR filters. When you design your FIR filter in the real world, there are a longer list of more important parameters that make FIR filters slightly harder to design than what you've seen in the last previous lectures. So, lecture, we will look at how the FIR filter can be implemented on hardware. Please like and subscribe and comment any questions below, and I will be happy to answer them. Thank you. See you next time.